All right, ladies and gentlemen, class recording has started. So, yesterday, we introduced Newton's third law. Before we review Newton's third law, let's review Newton's other two laws, right? Newton's first law is what? Inertia, right? Things don't change unless we make them change. Newton's second law deals with acceleration. We talked about the two things that affect acceleration, net force and mass, right? Newton's third law, what do we use to summarize the idea of Newton's third law? Action, reaction, right? If we apply force to an object, that object applies force back to us. Same magnitude, different direction, right? So let's fill in the top of today's outline, right? Newton's third law. When one object exerts a force on a second object, that second object exerts a force back on the first that is equal in magnitude, opposite in direction. This is like exactly the same from yesterday, so if you want to fill it in as like review, that's great. When one object exerts a force on a second object exerts a force back on the first, equal in magnitude, opposite in direction. What do we call these equal and opposite forces? We call them action-reaction forces or action-reaction pairs. Sometimes you'll see that, okay? Action-reaction forces are equal in magnitude, opposite in direction. And there's one more thing that we talked about yesterday that's really important about action-reaction forces. Equal in magnitude, opposite in direction, and there's one other really important thing that we talked about yesterday. Do we want to let Jack answer all the questions today? Yeah. Sorry, go ahead. They don't cancel each other out, and why don't they cancel each other out? They don't act on the same object, right? So action-reaction forces are equal in magnitude and opposite in direction. But they don't cancel each other out because they act on opposite or different objects. Good with those basics. Okay, let's use this idea to oh, there it is, act on different objects. Did I leave you a third spot there for act on? Maybe go ahead and throw that in there, right? That's kind of important. Okay, that would be right. So that would just be right underneath, yeah, right underneath number 2, right? Act on different objects. All right, good there? Okay, so let's use this. Oh, we did this already. Okay, let's use this idea when we talk about another concept that we refer to as conservation of momentum. I don't know if you remember or not, but way back on like the second day of school, we talked about some of the big ideas of physical science. Big thematic things that we see in lots of different areas applied in lots of different ways. Conservation is one of those ideas. It's a big thematic idea that we see applied in a lot of different applications. Applying something in applications, that's using applied too many times in the same sentence, but you get the idea, right? So, when we say something is conserved, what does that mean? Right, good. It's saved, right? Or it stays the same. So when we use conservation and apply it to some other concept, it means we keep that thing the same. So when we talk about conservation of momentum, that means that the total momentum will never change. And we use this mathematical equation to represent the idea of conservation of momentum. So you can just put this right next to conservation of momentum on your outline. So Roman numeral 1 Roman numeral 2 where it says conservation of momentum, right? Sigma pi equals sigma pf. Okay? Check, good. Yep. Yep. Now, you'll see that there, like when we look at actual formulas, there's not really that many, right? You got F equals ma, and then we got momentum, impulse momentum, and then this one here with conservation of momentum. So, say again? Yeah, I'll come to you like, okay, this is Newton's second law. So let's talk about this equation. First, we've learned these symbols before. What does the sigma mean? The sum or the total. So when we talk about sigma pi, well, what does the p mean? Psst. So sigma means sum. What does the p stand for? Not the change in momentum. The p itself just stands for what? Momentum. If we throw the delta in front of it, then it's change in momentum, right? So, and then the I is going to represent what? Initial. So sigma pi means we're going to add up all of the momentum of all of the objects that are involved in a situation at the beginning of that situation. What does sigma pf mean? The sum of all the final momentums, right? So, what this equation says is, if we look at the total momentum at the beginning and the total momentum at the end, it's going to be the same. And that's the idea of conservation. That whatever we start with, we're going to end up with. So in the case of conservation of momentum, when two objects interact with one another, so here, much like Newton's third law, if we're going to look at conservation of momentum, we have to look at an interaction. We can't just look at one object. We have to look at two or more objects that are interacting with one another. When two objects interact with one another and apply action-reaction forces, momentum is conserved. But that only applies when we have something that we call a closed system. And we'll define that here in just a little bit of what that means. Okay? All right. Good with this definition. Before we start talking about applications of this idea, let's review some concepts that we're going to need to have moving forward. If you would please, grab out the packet that I gave you, and we're going to start right on the front page with the one that has the cannonball on the front of it. And we're going to answer two questions. The first two questions. So it says, a moving car has momentum. If it moves twice as fast, its momentum is twice as much, right? Because how do we calculate the momentum of an object? Not mass times the change in velocity. That would be the change in the momentum. How do we calculate just the momentum of an object? Mass times velocity. So if we're talking about a single object and its momentum, we take that object's mass, multiply it by its velocity, and that gives us the momentum. So if a moving car has momentum, if it moves twice as fast, its momentum is twice as much, right? Two cars, one twice as heavy as the other, move down a hill at the same speed. Compared to the lighter car, the momentum of the heavier car is twice as much, right? Momentum is directly related to the mass of an object, but it's also directly related to its velocity. Okay? Good there? Okay. These questions apply to singular objects. We can talk about the momentum of some separate object. But when we talk about conservation, we have to talk about interactions. Okay? So, let's take a look back at the outline. And let's talk about this interaction. Okay? All right. So perhaps you've seen this before. Hopefully you have, right? Someone playing billiards. Doesn't it sound like fancy when you call it billiards instead of pool? You know. So let's be classy and sophisticated today and call it billiards. So. All right. So here we are. Billiard player hits the cue ball, which is letter A, into the 3 ball, which is letter B. If, and perhaps you've done this before, right? If you hit the cue ball just right, you can make the cue ball stop and you can make the other ball go, right? And you can make the cue ball stop right dead at the collision point, and then the other ball takes off, right? because this is an interaction, we should see conservation of momentum here, right? And the idea behind conservation is whatever we have at the beginning has to be there at the end, right? So, these two would be the individual momentum of each object before the interaction. So PAI is equal to M times V, and PBI is equal to M times 0. Because what is the B ball doing before the interaction? Nothing. It doesn't have velocity, so it doesn't have momentum. If we added these two together, what would we have? No. No. What would we call the sum of those two quantities? Sigma P. No. So this would be sigma Pi because Chris, is this before the interaction or after the interaction? This is before, right? So this is sigma Pi if we add these together, right? That being said, that would be the momentum after the interaction, right? If we make the cue ball stop and the 3 ball go, now all of the momentum has been transferred from A to B.
The velocity stay the same?
It depends. So Jack says, would the velocity stay the same? And the answer is it depends. What does it depend on? Nope. Just in this interaction right here. So when the 3 ball leaves the cue ball, what does it depend on if the mass if the velocity was in? Nope. Nope. What about the cue ball? There's something about the cue ball. Actually, it's something about both of them. Nope. The velocity would be the same if the masses were the same. Because what is the conserved quantity in this interaction according to the title of the slide? Momentum is conserved. And momentum depends on mass and velocity. So Jack, in this case here, the 3 ball would come out of here at the same speed as long as the mass of these objects was the same. All right? Good there? Oh, well, let's do this. I'm actually, this is, yeah. Sorry, squeaky shoes today. Okay. Okay. So, here's red. At least I won't slip. All right, here's red, here's blue. Okay? So, if I take red and push it into blue, what should we see happen? The magnets are in those, yeah. They are facing the same, yes. I'm not trying to trick you with this one. I'm just trying to illustrate this example here, okay? So, red's moving, right? Blue's not. Red has momentum, blue doesn't, right? Well, here, let's do this. Okay, ready? Here we go. Okay? Red had momentum before the interaction, right? Blue has momentum after the interaction, okay? All of the momentum of red was transferred into the momentum of blue. How fast did blue come out of that interaction? As fast as red came in. Why? What's true about the two cars? Mass is the same, right? Okay. This silver bar has approximately the same mass as the cart itself. Okay? So, if red comes in and blue goes out, what should we see about blue going out? Be slower. If we double the mass, how much slower should it be? Twice as slow or half as fast, right? Okay? All right, are we ready? Here we go. Now, actually, let's do this one, because that one's not quite the same. So. Okay? So, now, red's going to be moving with twice as much mass. Right? So now it has twice as much momentum, because the mass increases, the momentum increases. How is blue going to make up the difference? It's going to go faster, right? It's got to go faster to make up that difference, right? Ready? Here we go. Okay. How much heavier is blue, or how much heavier is red now? Well, it's 4 times, right? Because it's got the cart plus 3 silver bars. That's 4, right? Because the cart itself is 1. So what does that mean about how fast blue should be coming out of here? 4 times as fast, right? Ready? Here we go. Now, was blue actually going 4 times as fast? No. How do you know that? What evidence do you have to suggest that? Red didn't completely stop. So was all of red's momentum transferred into blue? Wasn't. Okay? If blue was going faster, right, it wouldn't be 4 times as fast because it doesn't have all of that momentum. Some of red's momentum still stayed with red. So at the beginning, red had momentum and blue didn't, but at the end, both red and blue had momentum. Does that make sense? All right? Yeah, go ahead.
So, if like, since friction stopped it?
Friction didn't, well, friction stopped it when?
From
Yeah, when it gets off the, when it gets off.
Does friction have momentum then?
Well, friction is a force, so forces don't have momentum, right? So, but would something else have momentum? Yeah. Right? And it gets back to, oh crud. Sorry everybody. I was gonna look up the calculation I did for the people jumping on the earth, and I thought of it last period, and then I started doing something else and I forgot. So, my bad. Jack, by stopping when it hits the towel that's sitting on the desk, technically that cart now has become part of like the earth. Does that make sense? So now that earth would have a little bit more momentum, but because its mass is so big, its velocity is so small. Okay. All right, good there? All right, let's do this. Ready for the next example? Okay. So, what's the total momentum here? No, just one spring is good because one spring will push off of the other one. What's the total momentum here? 0. Neither object has momentum. Does that make sense? Because both of their velocities are what? 0. Right? But when I let it go, what's going to happen? So, we went from 0 momentum to both objects moving. Do both objects have momentum then? Yeah. So was momentum conserved in that interaction? What is the idea? What does conservation say? Has to stay the same. What was the momentum at the beginning? Zero. Neither one had momentum. We let them go. What started happening to both of them? They both had momentum. Say again? Now they don't, but we're looking at like right when they push off of each other. Because now they're interacting with other stuff, frankly. They get, once they get off the track, this doesn't apply anymore because now they're interacting with other stuff. All right? So, just like this situation we talked about yesterday with striped girl and blue girl, is this conservation of momentum? And the answer is it might not look like it, but it is because, and I'm sorry, it's being hidden right here, because of the vector nature of momentum. If we say momentum has a vector nature, what does that mean? Magnitude and direction, right? The total momentum at the beginning, before striped girl and blue girl are moving, is what? Before they start moving, the total momentum is 0, right? After they start moving, blue girl is going to the right, striped girl is going to the left. What does that mean about their momentums? How would we distinguish between them? One's positive and one's negative. When we add them together, what's the total end up being? 0, which is just what we started with. Does that make sense? You start with 0 and end with 0. Is that conservation? Do you end with what you started? Yeah, you do. That's conservation, right? If I do this, right, here's red and blue again, but now I add one silver bar onto red, right? Okay. What should happen when I let them go? Blue will go faster than red, right? How much faster did blue go than red? Twice as fast, right? Because we need to have the same amount or the same magnitude of momentum, but the direction is different. Good there? Yeah? So, let's go back to our page that we got today, and let's go to the third page, which has these two springs, which look very, very similar to our two cards. All right. When the compressed spring is released, blocks A and B will slide apart. There are 3 systems to consider. Now, I told you that momentum is conserved in a closed system. A system is just something we look at. So there's 3 systems here, indicated by the dashed lines. We've got system A, or block A by itself, system B, which is block B by itself, or system A plus B, which looks at the whole thing, right? I told you that conservation of momentum applies when things interact. So which system should we see conservation? System A plus B, because it's the only one where things are interacting. So, does a force act on system A? Yes or no? Yes, it does. Where does it come from? Yes, but when the spring needs something to push against, right? So the system A feels a force from B, right? Will the momentum of system A change? Yeah. Force causes changes in momentum, right? Impulse, yes. Individually, system A changes momentum. Does system B feel a force? Yeah. If system A feels a force, if block A feels a force, does block B have to feel a force? Yeah, according to what? Which law? Newton's third law, right? If B pushes on A, what automatically happens? A pushes on B. So will system B's momentum change?
Yes.
Yes, it will. Oh, sorry, my bad. Give me a break, everybody. Sorry. All right. There are forces, but when we look at system A plus B, everything inside this dotted line. Okay? A feels a force from B, B feels a force from A. Are there any external forces? No. In this system here, A pushes on B, B pushes on A. Those are what we refer to as internal forces. Internal forces will, or so, does an external force act on system AB? The answer there is no, as long as what's true about this table that they're sitting on. There's no friction, right? Friction would be an external force. In this case here, right, or in our track, we have pretty low friction.
What about gravity?
Gravity is an external force. Gravity's pulling down, right? What else is happening to those blocks, though? A normal force, the force from the table is pushing up, so what happens to those two? They cancel and nothing happens from those two. Okay? So, will the momentum of system A plus B change? Not of the system. Individually, yes. But when we look at how much A changes and how much B changes, they're exactly the same, but in different directions. So we end up with whatever we started with at the very beginning. Okay? Good there? We okay with that idea? All right. So let's put some numbers on it. Let's go to page 2 of that packet, and let's look at this picture of Granny and Ambrose. Okay. Yeah, Ambrose. All right, so let's do a couple of quick calculations. They're pretty easy calculations, right? So it says Granny whizzes around the rink and is suddenly confronted with Ambrose, who is at rest directly in her path. Rather than knock him over, she picks him up and continues in motion without slowing down or without braking. So first, the fact that Granny is roller skating is pretty cool, but then the fact that she could pick up a small child while she's roller skating is quite impressive in itself. All right? So it says, consider both Granny and Ambrose as two parts of one system. Right? Remember we talked about system A, system B, and system A plus B? Right? So in this case, we can think of Granny as system A. We can think of Ambrose as system B. Okay? Complete the before and collision data in the table below. So Granny has a mass of 80 kilograms. She's going at 3 meters per second. What is her momentum going to be? It's going to be 240. Does everyone see where that number came from? If you don't understand, raise your hand. Don't be a chicken. We know that momentum is m times v, right? All right. Ambrose's mass is 40, but his speed is 0. So what's his momentum? 0. You have no velocity, you have no momentum. So the total momentum, right, of Granny plus Ambrose is going to be what? 240. Kilograms times meters over seconds. Okay? All right, good there? So now let's look at the after, right? So now, Granny and Ambrose, even though individually they were their own systems, right? Now, they're all one big system. Okay? What does the total momentum of that system have to be? 240. All right? What's going to happen to Granny's speed when she runs into Ambrose? It's going to decrease. She's going to slow down. But what's going to happen to Ambrose's speed? He's going to increase. Right? He was not moving, now he is. After the collision, now that they're one big system, what is the mass of that system? 120. Because all we did was add together Granny's mass and Ambrose's mass, right? After the collision, the total momentum of Granny and Ambrose is 240. All right? So, we know that Granny and Ambrose have to have a momentum of 240, but now, because they're held together in the same system, their mass is 120. So, what will be the speed of Granny and Ambrose? Alec? 2 meters per second. Do we see where that came from? How do we calculate the momentum of something? Okay. Notice I'm working as purple here, right? In this case, we want the final momentum, the final mass, and the final velocity. We know that the final momentum of Granny and Ambrose has to be what?
240.
Has to be 240. Because Granny and Ambrose are together, their mass is 120, and then the only thing we don't know in that equation is what their final velocity is. Does that make sense? So to get v by itself, what are we going to do? Divide both sides by 120, and that gives us a new speed of 2 meters per second. All right, good there? Okay. Tomorrow, we'll do one more example at the beginning of class, and then you'll get started on your conservation of momentum lab. Yeah.